Hello guys, welcome back to Maths on African Motives, still on our mathematics and 5 working on the integration. This is another part that we're going to have as a continuation from the previous part that we talked about. We worked on the area, talking about the area that is between a curve and the reference axis, whether you're talking about the x-axis or we're talking about the y-axis, talking about the area. That is going to be found between a curve, between two given curves in this case. All right. So in this class that we're going to have now, we're going to be focusing on the volume, which is a continuation from the area that we had. So we are going to see that the area that we calculated before, this time it is going to be rotated. So we're going to rotate the area. So the application of the volume is to rotate the given area, all right? That is to rotate the area that we used to calculate previously. So meaning to say the application of the area is still considered in this case, all right? So we are rotating the area about a certain axis or referring to a certain axis that we can be given. It can be given about the x-axis or it can be given about the y-axis. So it's a rotation that is going to take place of the area about the x-axis or in the y-axis to give us the volumes that will correspond to what we are talking about. All right, so this is the application that we're going to have. So we're going to just have the first part, just calculating a normal volume from the area that is bounded by a curve and a reference axis. So what I just need you to have are the formulas that we are going to be focusing with so that we can just do the calculations. As we saw the diagrams, I talked about these diagrams from area. So here I'm just going to write the formula so that we quickly check the questions that we might be given. All right, so the first part, like I said, we are going to have the condition of the volume of area of the volume of the area bounded by a curve. All right, so this is going to be bounded by a curve. All right, so we're going to have this bounded by a curve and a reference axis and a reference axis. So this is what you're going to have in this case, all right? And a reference axis, meaning to say the reference axis can be the x-axis or it can be the y-axis. So we can have a condition where we just have a single curve, not two graphs. We are just given one graph. So we are going to calculate the volume of the area rotating in the x-axis. So we're going to have this area rotating in the x-axis, all right? So when it is rotating in the x-axis, remember from our calculation of the area that we talked about, we saw that the area was going to be given, the area with respect to x is going to be given as the integral of y with respect to x given the limits a and b. So if it is for the volume in this case, all right, the volume that we are going to calculate with respect to x is going to be given as pi times the integral of, so this y that we see this time is going to be given as y squared, all right? So that's with respect to x with our limits a and b. Remember y, we said it represents the function of f of x. So the function of x, so that means the same thing with this y here. It's a function that we're gonna have in terms of x so that we can be able to integrate with respect to x, whatever that we're going to be given there. So it is the same concept that we are going to see if we are rotating about the y-axis as we saw from our diagrams. So this part I'm just going to have a continuation. So we're going to have the volume of area rotating up in the x-axis or about okay, this time is the y-axis, all right? So in the y-axis. So we are going to have this in the y-axis, so the volume is going to be given. Remember, the area with respect to y was just integral of x with respect to dy. So that means in this case, we are going to have the volume as pi times the integral. Instead of having x, it's going to be x squared. All right, so remember, x represents the function of y, just like this y here. It's a function of x. So it is going to be the with respect to y in this case, all right? And remember, our limits are explained previous when you are given a curve affected in the y-axis. We've got the limits c and d in that case, having a representative strip of the y-axis, all right? So that just make sure you watch the introduction of the other part of the area. It's just a continuation from there. So this will be the point, the limit c and the limit d. So this we are simply referring to the function of y in this case, all right? So x is a function of y. This y here is a function of x. So that is the whole idea, so that you are going to integrate with respect to x. Here you integrate with respect to y. So if with this idea, you can also see that if you are now given a condition of the volume of, we are going to have the same thing of the volume of the area bounded by the two curves. Here we had a condition of the volume. All right, so this is just 1. So let us just put this as 2, not C, but let us just put this as a 2. So we are going to see that we have a same condition just like in area, whereby we had a condition of calculating the area of the two curves. We are given two curves. You are calculating the area bounded by the two curves. It is the same thing with the volume. All right, so you're going to have this time to calculate the volume. So you're going to have the volume of the area. So let us just have as a subheading the volume of the area bounded by two graphs. All right, so this is bounded by two graphs. All right, so that is the most important part that we're gonna have in this case. All right, so these are graphs, or you can just have these as the curves in this case. All right, which is a function that you're given of any part. It can be algebraic, an exponential, a trig, whatever type of function that you're given. So this will be referred again with the reference axis. All right, so we are going to have this and the reference axis. So just like the previous part that we had here, we referred or we talked about the reference axis. So also here we are going to refer this one and with the reference axis, all right, and the reference axis. All right, so this is what we are going to have in this case, all right? So meaning our reference axis can be the x-axis or the y-axis, just like what we had on the calculation of the area just bounded by the curve, and the volume of area bounded by the curve, and what the reference axis. It is the same thing as of the volume. So meaning to say we shall have the same thing rotating in the x-axis, or it will be rotating in the y-axis, all right? So rotating in the x-axis, what is going to happen in this case? Remember, on our area, we talked about this, that if you're given two curves like this, you're going to consider y1 on top and y2 below. That is given with respect to x. So it is the same thing that you're going to have in terms of your volume in this case, the volume with respect to x, but this time, remember, for volume, we're going to multiply with I. So you're going to have the difference between the upper and the lower in this case, but being squared. So that will be y squared minus y squared. So that is y1 squared minus y2 squared with respect to x. So this y is a function that we have of x. It's a function of x. So that means we are going to integrate with respect to x with our limits taken as a and b. So like the condition of the area, remember that a and b, these values are the ones that we obtain at the point of intersection of the two graphs or the two curves that we are given in this case, all right? So it is the same thing that we are going to have when rotating about the y-axis. So we're going to rotating in the y-axis this time. So just like what we had on x, we shall have a difference of x1 and x2 being this our x1 and this being our x2. So it's the upper part minus the lower part, this one on the more positive, this one on the negative side. So that's going to be x1 squared. So we're going to have our formula as Vy is equal to pi the integral of, so it's going to be x1, which is the upper part, x1 squared minus x2 squared, all right? So as we know that x is a function of y, so this will be integrated with respect to y, and the limits will be taken at C and D. For the y-axis, we're going to use C and D, right? For the x-axis, just going to use A and B, but you can choose to write the way that you understand, as long you know that these are the limits that are affecting the y-axis and taken at the point of intersection of the two graphs that you'll be given. All right, so with these formulas, you can see it's all that we actually gonna need in the application of our volume. So just want to check a few questions on the application of this, and maybe as time goes on, if we're gonna have time, we are going to work with the full question papers, like work on exact part that we talked about. In this case, if it is volume, we work on question papers just on the volume part, so that you'll be able to understand how these questions are given. All right, so with me here, I'm just gonna focus with one or two questions that we want to apply with the formulas that we have on top. So let us just say we're given a question in this case. All right, we've got a question in this case to determine the whole of this part is going to be determining of the volume in this case, right? So we are going to be determining, that is determine the volume. So that is our question there, determine the volume generated. So the volume is being generated, all right? When the graph or the area, when the area in this case bounded by, so that is our question there, area bounded by. All right, so let us have the first one. So the first one, let's say we are given just a simple question, y is equal to 3x plus 1, that is our graph taken between the x-axis. So let's say it's taken between the x-axis and also the point where x is equal to 6 and is rotated about the x-axis. All right, rotated about the x-axis. So that is the condition of our question. If we are to check in our syllabus, we just calculate our volume in a direct manner. So we are not going to expect anything so special that we have, unless we've got N6, whereby we shall be talking of different methods of calculating the volume, the disk method and the shell method. So we shall see those ones, the difference between the two. But in this case, we're just focusing with the direct method that we know as a disk. All right, so given in this case, to calculate the volume, take note, it's bounded between the line. This is a straight line of y is equal to 3x plus 1. Just like what we had on area, it is best for you to just have a sketch so that you see what is happening on the graph of y is equal to x plus 1. Before we talk about this, all right, so let us just have the sketch of the graph in this case. All right, so given the graph of y is equal to 3x plus 1, that's a straight line. So we can just focus on determining two important things in this case, which is the x-intercept and the y-intercept, and also to know, as we can see, it has got a positive slope, positive gradient. So meaning to say our line is going to be either in this way, or we are going to have it maybe down, but having a positive gradient that is going in the positive way. All right, so by determining the x-intercept and the y-intercept, we can know where our graph is going to pass through. All right, so for the x-intercept, as we know that y should be equal to 0 at that moment for us to find the x-intercept. All right, so you're going to transpose the -1 to this side to be +1 to this side becomes a -1, which is equal to 3x divided by 3 by 3. So that's our x is going to be a -3. All right, -1/3 as a value of x. Maybe you're talking about a value that is somewhere here, -1/3. Okay, we do the same thing for the y-intercept, where we know that x at that moment must be equal to 0 in this case, right? So for the y-intercept, it is x this time that is equal to 0. So that means y is going to be 0 plus 1, which is 1. So this time we are going to see our graph passing through the y-axis at a point 1, maybe somewhere there, which is a positive. So we can just join our graph in order to complete this straight line. So we're just going to join the points minus a third, passing through 1. So this must be a straight line, all right? You're supposed to use a ruler, draw your straight line properly. Then you just write your equation, y is equal to 3x plus 1. So that is the condition of our question in this case, or the condition of the graph. But now if we are to consider, they are saying, we are supposed to determine the area, yes, which is the volume, which is fine. But where is it taken? The x-axis has to be considered as we are having between this line, because it has to be bounded, it has to be covered by certain lines in this case. All right, so it has to be covered, this volume. So this volume, it has to be covered by 1. The straight line of y is equal to 3x plus 1. The x-axis. So the moment we mention about the x-axis, we are talking about being here. So we're talking about this part is included on our area, on our volume, I mean, and the line is involved. This part is involved. All right. We move on. The line x is equal to 6. So we must have a line called x is equal to 6 like this. So as you can see, the part that is going to be left is in between, which is this region covered by these lines. That is from what? The line of y is equal to 3x plus 1, the x-axis, and the line of x is equal to 3. So x is equal to 6, maybe is somewhere here. That is where we have the point 6 that we remember. The equation x is equal to, like this one, it's x is equal to 0. So x is equal to 6 is going to be a vertical line. So this is the equation of the line. So in order for us to calculate the volume, as we can see, the part that is being left bounded by is this part here in between. So we are going to calculate the volume there, and we are given about the x-axis. So meaning to say, we are going to have our representative strip in the x-axis like this. All right, so you're going to just calculate. So using the disk method is just a direct calculation of the volume that you have with respect to the axis that you are given, and also bounded by, as we can see, this line, the x-axis, and x is equal to 6. This is going to be covered up to minus a third. So meaning to say, if you're talking about this region here, so the limits that you're going to have, it's minus a third at this point and positive 6. All right, so that is where we are going to consider our volume in this case. All right, so this is the part that we're talking about. So this volume will be generated so that at the end we formulate a cone, this and that. That one, if you want, it's just for you to understand. But what is important, the moment that you show this, you just want to know the limits in this case, to say this is minus a third, this is a positive 6. And I have to calculate the volume direct, because here I'm just given a line, which is the graph with the x-axis that I'm given. So that means the volume that I'm going to calculate, it will be with respect to x. All right, so the volume with respect to x, remember, on a single graph like this, we said it is going to be given as y squared dx. So it's the integral of y squared with respect to x. It's rotating in the x-axis, and it's just the area bounded by the curve and the reference axis. With this one, it's not between two curves or two graphs. So meaning to say, we are going to have our volume with respect to x as pi, the integral of y squared with respect to x, taken our limits as a and b. All right, so that's our volume. So y is a function of x, which means we're talking about our f of x, which is 3x plus 1. So that is going to be pi, the integral of 3x plus 1 like this to the exponent of 2 with respect to x. All right, having our limits from minus a third, which is our lower limit, to positive 6, which is the upper limit in this case. All right, so we can be able to integrate this. So you see the advantage, guys, of knowing your laws, these rules of integration. I think I tried by all means to separate them in a way that we understand. Yes, we can expand the brackets. I want you to do that. If you can expand the brackets, you can do that here. You expand your brackets, you integrate after that, then you substitute the limits. But remember, I talked about the integral of a fraction, well, I mean a bracket like this. how do I integrate this part? All right, so here, remember the integral, you have to add 1 on the exponent, which is the opposite of the derivative where we subtract. So on our exponent of the bracket, we are going to add a 1. So let us just have the integral of ax plus b like this to the exponent of n with respect to x. All right, so this is going to be ax plus b to the exponent of n plus 1 from the integral part. So it's going to be n plus 1 over n plus 1. All right, but what is going to happen is that this part here is going to be found, we are going to find its derivative, this a, the ax. So you're going to find the derivative of ax, which is a, and you multiply by 1 over a. So in actual sense, we are going to see on our formula written as a into n plus 1. What is actually happening is that we multiplied by 1 over a. So if you consider that integral, in short, we can see that Vx is going to be given as pi. Then we integrate this 3x plus 1. So it's going to be 3x plus 1 to the exponent. We add 1, just like n plus 1, which is going to be 3 over, we multiply the 3 that we got from the integral. But here we find the derivative of this. It was supposed to be 1 over a, which is 1 over 3 like this. That is what we're supposed to have in actual sense. All right, so this is having the limits 6 and minus a third in this case. All right, so that is how we can simply integrate this. Like I said, you can expand the brackets, still it's fine. You're going to obtain the same answer, expand your brackets, integrate each and every term. So here we just integrated directly by knowing this formula. All right, so that means we are going to have our Vx as, if you multiply 3 by 3, that's going to be 9. 1 times this bracket is not going to affect, so it's just going to remain as 3x plus 1 to the exponent of 3 over 3 times 3, which is a 9 in this case. All right, everything to the exponent of 6 minus a third like that. All right, so there we can just substitute our limits. As we can see, we've got the upper limit in this case, and this is our lower limit. So we're just going to substitute in this case. All right, so that is our Vx is going to be pi into, we substitute the value of x on the upper limit, it's 6. So it's going to be 3 times 6, which is 18, or you can just multiply 3 times 6 plus 1. All right, this is being raised to the exponent of 3 over 9, right? So this one is awkward here. So let us just write as a single term. Like I said, we substitute 6 here. That's 6 times 3 is 18. So that's 18 plus 1. At least this one can make sense. All right, we do the same thing on the lower limit. So it's going to be minus. We do the same thing for the lower limit, which is minus a third. So if we substitute here, it's going to be 3 times minus a third. All right, so that is going to be a -1. So it's -1 plus 1 over 9. All right, but this is being raised to the exponent of 3 like this. Right, so this is what you're going to have. So as you can see here, we're going to have a 0. So that means there's nothing that you're going to have. So we just have to simplify this part here, which is going to be 19 to the exponent of 3 over 9. All right, and that is going to give us something like, all right, let us check. We simplify properly. You can ignore this pi. All right, you can just ignore this pi here. So if you ignore this pi, you simplify this part, you're going to have 6,859 everything over 9 like this. All right, so that is what you're going to have, which is the same thing as 6,859 over 9 pi like that. All right, so volume is measured to the exponent of 3, that is units to the exponent of 3, or you can just write as cubic units like that. Right, so that is the units of volume is the cube in this case. Right, so that will be to the exponent of 3. And also you can just simplify this directly. All right, this as it is on your calculator. If you simplify, this will be 239 4,243. All right, which is units to the exponent of 3. Or you can just leave it in terms of pi. or you can have also a decimal for pi, this decimal only, then it affects pi. You can write it in a way that you want, as long you understand what you are writing at the end. All right, so this is how we can calculate our volume when we are just given a curve and the reference axis. So in this case, we are working with the x-axis as our reference axis. All right, so let us consider another question. Let us just say we've got this time the y-axis as our reference axis. All right, so let us just save another question here that we can consider. I'm just going to focus with the same question that we had, like overall question, but the question here I'm just going to change it so that you can see the difference that we are talking about, but it is just one and the same thing that we had from this previous question. So this time, let's say we've got the graph of y is equal to ln x and bounded between the line x is equal to 0, the line of y is equal to 0, and the line of y is equal to -3. All right, and it's being rotated, this one, it's being rotated about the y-axis, all right, about the y-axis in this case. All right, so let us see. It is being rotated about, it's just a single curve. So we shall see the formula for volume. We talked about this previously about the formula, but what I'm focusing on is on the sketch. So remember, you are supposed to sketch this graph of y is equal to the ln of x. So how are we going to sketch this graph of y is equal to ln of x? And also we present our rotation about the y-axis. All right. So remember from our graphs, because yeah, it's just a continuation that we had, guys, from our mathematics N4. We talked about the logarithmic graph in this case, right? Talk about the logarithmic graph of this nature. From our logarithmic graph, we're going to have the x and the y like this. So remember, for log, we do not have negative value. We cannot have negative value here. Log cannot be negative. It's going to be always positive. All right. So, and also we do not have the value for log 0 at this point. So it's an infinite. These values for 0, they do not exist. It's actually infinity values. All right. So our log is going to be only taken from the positive, and we know that the log of 1 is equal to 0. If the log of 1 is equal to 0, it means our graph is just going to be like this, passing through the point 1 at this point, which is 1 versus 0. So this is the curve that you're going to have to expect for a graph of log y is equal to ln x. Just also check the graphs for mathematics N4. I think we talked about this, so that you can have a recap on sketching of the graphs and so forth. All right. So having your graph of y is equal to ln of x, we're given this must be bounded between this graph that we are seeing of y is equal to ln x. The line x is equal to 0. The line x is equal to 0 is the y-axis. The line y is equal to 0 is the x-axis. So we've got the x-axis being there. I mean, the y-axis being there, the x-axis being there, this curve being there like this. So as you can see, we are left with this part. It's either our area is going to be here, it's either our area is going to be here, or it's either our area is going to be here. So that's where we have a final solution here. And y is equal to -3. The line of y is equal to -3 is somewhere here. So it means at the end, the area bounded is this one in between that we are going to have at the end, right? So these are the points that we are going to have at the end. So as you saw that we're gonna need the line of y is equal to -3 at this point. Y will be equal to -3, right? So that's at this point here, y is equal to -3, which is the one that is going to bound the graph. So it's now covering the graph. The line of x is equal to 0, the line of y is equal to 0, and the line of y is equal to -3. So this is the region that is left that we must focus on. All right. So as we can see, our representative strip, we've got the limits in the y-axis. All right. So we're going to have our representative strip in the y-axis. So that means we are going to have this way. All right. So that means we can be able to calculate our volume. Remember what I said, the volume with respect to y in this case can be taken. All right, we can just go back here that is be x squared with respect to y, right? That is rotating in the y-axis. So that will be pi integral of x squared with respect to y. Our limits being taken between c and d in this case, right? So that means here we're going to have our formula pi, the integral of x squared with respect to y with our limits c and d. So the limits c and d are the limits that we have in the y-axis. That is, we've got S0 here. All right, we've got S0 here, and we also have a -3. These are the limits. But if we check our equation, this one, it's written y is equal to not x. So we must write this equation in terms of x. So what we simply need there is to make x the subject, full stop. That is what we simply need. We are simply going to make x the subject of the formula because we are given this in terms of y. But here we need x. So we are going to make x the subject. If y is equal to the ln of x, it means the ln of x is also equal to y. Just the same as a is equal to b, b is equal to a. So I haven't changed anything. So we're just going to write the ln of x is equal to y. But remember that a ln is a log. The ln of x is equal to the logarithm of x in base of e. So whenever we see this ln, we see a log with the logarithm of x in base of e is equal to y like this. All right, the logarithm of x in base of e is equal to y. So with this part that we are seeing, we can now make x the subject. Remember, from our logarithms, we can have a conversion that we can make from a logarithm to an exponential. The logarithm of a in base of b being equal to c. It means this a is equal to b to the exponent of c. So that means this x that we are seeing here representing a must be equal to the base, which is b to the exponent. So that is our base, which is e to the exponent of y in this case. All right, so this is e to the exponent of y. So we have the equation in terms of x, all right? That is as x being the subject of the formula. So x is equal to, we saw that x is equal to e to the exponent of y in this case. So that's how we can simply, but as you can see, we are not even supposed to have all these steps. If you actually know your logarithms, exponents, I don't even have to go through all these writings that we have. We just have to write the answer direct. So it is very, very good that we just revise towards our exams like this. All right, so the volume with respect to y is going to be pi the integral of x squared, whereby x is the function of y, which is e to the exponent of y in this case. But this is being squared, all right, with respect to y. And the limits we mentioned, the limits in the y-axis is going to be -3 to 0. So that's -3, 0 like that. So that means we can be able to simplify and find the integral, just like our normal integrals. If you're dealing with an exponential, all right, this will be pi the integral of, we can multiply 2 times y there, which is e to the exponent of 2y with respect to y, in this case with our limits, -3 versus 0 like that. All right. So remember that the integral of e to the exponent of f of x with respect to x is simply e to the exponent of f of x over the first derivative of x of x plus the constant. So here I've got f of y in this case. So we simply need the e part as it is. So that is the exponential part as it is e to the exponent of 2y. That is e to the exponent of f of x from the original function over its first derivative. So here we need the derivative of f of x, which is f of y in this case. So f of y is 2y. So what is the derivative of 2y? That is 2. So we are going to have over 2 like that. All right, the limits being 0 and -3, right? -3 being the upper limit, the lower limit, and 0 being the upper limit. We can substitute, as we know, we're gonna have upper limit minus the lower limit from what we have in this case, all right? So let us just substitute our values and see what we are going to have at the end. So like I said, we are going to have upper limit minus the lower limit in this case. So that means our volume with respect to y is going to be pi into the upper limit being a 0 here. So that's e to the exponent of 2 times 0, guys. That's a 0 there, all right, over 2 minus the lower limit, it's -3. So you're going to substitute -3 in place of y. So that's 2 times -3, everything over 2 like this. All right, so that was going to give us the volume in this case, which was going to be something like 1,5669, which is 1,567. All right, square units, cubic units for volume. All right, it's gonna be cubic units there. All right, so let us just have that's cubic units, of which you can just write this as cubic units like that. All right, it's just one and the same thing. You can just have this in that manner. So if you're to check, if you are given a volume, guys, it's just a straightforward thing that you just need to work on, depending with the type of person that should be given. So we just need to work with more questions for your revision. It can be very, very important that you work with more questions as you are revising. Very, very important. All right. So if you have to take this into consideration, let us say for two curves that we are going to consider. Let's say all right, here it was area bounded by this and that. All right, this time we need two curves. All right, let's say we are given two graphs to consider, or two graphs to work with. We've got y is equal to 2x squared, and we have got the graph of x is equal to 16 y squared, like that. All right, being rotated about the x-axis, or maybe it's being rotated about the y-axis. All right, so it differs with the type of person that you are given. All right, so this case, let us say we are going to have this rotated about the x-axis. All right, so let us just have this about the x-axis in this case. All right, so having our curve, what we are going to have is to sketch. Remember, we just need to go back, guys, to our normal graphs, sketch your graphs, and so forth and so forth. So as you know, that graph of y is equal to x squared from the graph of y is equal to x squared. It's just a normal curve that you're going to have passing through the point is 0. So this one, we are going to have something of this nature if we are to have this as a sketch. All right, so that's passing through 0, going to the positive, as we know that for each and every value that you're going to have, we square it, it is going to correspond. So it will be symmetrical. We are going to have this symmetrical about the y-axis. That is, it covers about the y-axis. All right, so this is the graph of y is equal to 2x squared. We do the same thing, since here we are going to, all right, the other thing, okay, like I said, it's about the x-axis. So meaning to say we are going to consider our limits for the x-axis. So we must have this in the form of y is equal to, right? Y is equal, just like this, y is equal to x squared. So we have to transpose, all right? 16 is equal to x is equal to 16y squared, just divide by 16 there, that will be y squared is equal to x over 16. You can introduce the square root, so that's y is equal to the square root of 16. The square root of x we do not know, but the square root of 16 we know that is a 4. So as the subject of the formula, we are going to see that yes, we cannot have our x being a negative, but the square root of any number gives us a positive or negative number. So meaning to say, for any positive value, as long as we start from this 0 here, for any value that you're going to have in the positive, we are going to have a positive value and also a negative value for that value that you're going to have at the end. So it must correspond positive values and also negative values. Yes, you can just try to have your scale, a table of values to see how these graphs are corresponding, but know that the square root of any number is plus or minus. So there will be values on top and other values down. And as I said, we cannot have values in the negative. There's no square root of a negative number, unless you're talking about complex numbers here. We are not referring to complex numbers. All right, so that is the graph of y is equal to the square root of x over 4 in this case. All right, then we have to check between, because these are two graphs that we have. So as you can see, the area bounded, we can already see is the one between, I mean, the volume that we're going to have at the end is from this area that is bounded there. So from the area that is bounded, we know that we are going to have a representative strip here with respect to the x, since we are calculating in the x-axis. So the limits, as we can see, it will be at the point 0 here, bounded between, to the point of intersection at this point here, at the point of intersection. So we need the value that is going to correspond at this point of our intersection. So to calculate the point of intersection, guys, you just have to solve your equations. You just have to solve your equations. So what we need are the x values, not the y value. If you want to find the y values, you can do that. But in this case, we are focusing on the y values. So you can just take these two equations, I mean, on the x values. So we can just take these two equations. Y is equal to 2x. And here, y is equal to the square root of x over 4. So meaning to say 2x squared from this y here must be equal to the y that we have on this part, which is what? Which is the square root of x over 4. So we can cross multiply, then we remove the square root, or we can just remove the square root direct by squaring both sides. We are going to remove the square root. That's 2 to the exponent of 2, which is 4. X to the exponent of 2 to the exponent, we multiply 2 times 2, which is 4 in this case, is equal to, remember the square root of x squared gives us x over 4 squared, which is 16. Then we can cross multiply, or we can just transpose. If you want, you can just transpose this 4x to the exponent of 4 minus x over 16 is equal to a 0, like that. So we can factor out x, since x is common here. If I factor out x, this will be 4x to the exponent of 3 minus, if I factor out x here, I'll be left with 1 over 16, and this will be equal to 0. So as we can see, from the 0 concept, it is telling us that one of these brackets must be equal to 0. So that means x is going to be equal to 0, which is this solution that we see here already. We have got that. All right. Then the other solution is going to be from here. All right. So we're going to have 4x to the exponent of 3 will be equal to, if we transpose negative 1 over 16 this side, it is going to be positive 1 over 16. All right. So with a positive 1 over 16, remember, I want to find x, so we can divide by 4 both sides, because here we are multiplying, so we can just divide by 4. So this is 1 over 16 divided by 4. So we've got x to the exponent of 3, and this is 1 over 16 divided by 4, which is going to be 1 over 64 from your calculator. And then we're going to determine the cube root of this. So that means the cube root of 1 over 64 is going to be 1 over 4. All right, so that's the cube root, of which 1 over 4 as a decimal is same as 0.25. All right, so that's 0.25. So meaning to say, all this that we wanted to know, the point of intersection, the other part or the other value, where these two graphs are intersecting, it's at a point where x is 0.25. That's at this point here, where x is 0.25. So once I have this, guys, I'm able now to find the volume by what? By simply integrating, because we said the volume with respect to x is going to be given as pi. The integral of, we subtract these graphs. This is the upper graph on top. So that's our y1. The one that is below is our y2. So y1 represents the graph of the square root of x over 4. The graph of y2, which is this graph of y is equal to 2x squared. So that means our volume from the formula, we said is going to be y1 minus y2. All right, so you're going to have y1 squared minus y2 squared with respect to x. Our limits taken from 0 to 0.25, which is our a, and b. All right, so we're going to substitute this. That is pi, the integral of 0.25. Then we substitute our limits y1. Like I said, the one on top, which is this one on top, which is the square root of x over 4 in this case, squared, minus y2, which is this one below, which is 2x squared. All right, so this being squared, we are going to integrate this with respect to x. All right, so let's integrate, substitute our limits, we are done. All right, so that's it. Let's integrate there, substitute your limits, you are done. So Vx is going to be pi, the integral. Right before that, you can just simplify. Okay, let's just simplify before we integrate. 0.250 there. The square root of x squared. Remember, the square root of x times the square root of x is x. All right, then 4 squared is 16 minus 2 to the exponent of 2, that is 4. X to the exponent of 2 to the exponent of 2, that is 2 multiplies. So that will be to the exponent of 4 with respect to x. All right, so there we can integrate it. So you can see I've got a single term there. And as we know from our integration, we are adding 1 on the exponent and we divide by the new exponent. So that will be x squared. If we add 1 plus 1, that will be 2. So we're going to have the x as pi into x to the exponent of 2 over. So you divide by the new exponent, which is 2. So the 2 multiplies with the 16. So 2 times 16 will be 32. All right, minus we add 1 on our exponent, so that will be 5. So we're going to have 4x to the exponent of 5 over 5 in this case. All right, the new exponent, which is 5, with our limits, the upper limit being 0.25, the lower limit being a 0 in this case. So that's it. We can substitute our values, upper limit minus lower limit. Remember, that is how we are supposed to substitute back. So we're going to have our upper limit, which is 0.25. So that's 0.25 squared over 32 minus 4 into 0.25 to the exponent of 5, everything over 5 like this. All right, minus, as you can see, if we substitute a 0 here and a 0 here, that will be a 0 there, guys. All right, so that will be 0 minus 0 there. So there we have got the volume, which is going to be, right, we've got a pi there. There is a pi there outside. So that will be giving, it's going to give us something like 0.00368 cubic units or something like that. So as you can see, that is how these questions might be given. All you just need is to make sure that you work on your questions, revise on your questions to make sure that you understand exactly how your questions are given and how are you supposed to answer them. So that is our volume with respect to the x-axis. What if it was a condition that this time we want this volume the same set of graph, but having our volume about the y-axis? What was going to happen in this case? Let us just consider that. If we are to consider on our question here to say, this we said it's about the x-axis, right? That was our question here about the x-axis. But as I'm saying, let us consider the way that it was about the y-axis. What was going to happen in that case? In that condition, it means on this area that we have, or on the sketch, that the sketch is not going to change. What is going to change is the representative strip, because the area that the volume that we're going to calculate now is no longer with respect to x, it's now with respect to the y-axis. So the representative strip is going to change. We are going to have our representative strip this way to the y-axis in this case, all right? So that means you must have the limits corresponding to the y-axis. The limits corresponding to the y-axis will be taken at the point of intersection here, which is a 0. And at the point of intersection here, you must have the value of y that is corresponding there. So how do you find this? It is either you're going back here, you just like what we did, we make x the subject. I mean, you make the x the subject, you equate the values of x, like here, you make x and x, you equate them. Or you can just substitute, since we got that the value of x here is 0.25. So with the value of 0.25, I can substitute in any of these equations to find the value of y. So you can go back here. Y is equal to 2x to the exponent of 2. So I can just substitute there the value of y, which is the value of x, which is 0.25. So that is going to give us, that is going to give the value of y corresponding to that value, which is 1/8 or 0.125, like that. So that means the y value on the limit here will be 0.125. That is the value that you're going to obtain at this point. So meaning to say we are no longer focusing on what we had on the x-axis, this one. We are no longer focusing on this because we are saying it must be about the y-axis, and having this, we are going to focus direct. Yes, like I said, if you are to consider in your N6, we shall have a lot of methods, guys, that you're going to use. I mean, you're going to have extended methods, not a lot, but just extended to the shell method that you're going to use there, in also calculation of the volume. But here we're just going to calculate our volume direct, which is we're going to need the difference. Like I said, if it is with respect to y, meaning to say we're going to use x, our volume. With respect to y is going to be pi the integral of x1 squared minus x2 squared with respect to y with our limits c and d. So in this case, that is supposed to be x. Now we are no longer using this y2. All right, sorry for that. This y2, y1 that we had, it was for the limits that we had before. So this one is no longer focusing with this, guys. I'm just going to remove this. So we're going to focus with the x being the x1, which is the upper, this one, which is on the more positive. All right. So that will be your x1. And this one on the negative side becomes your x2. All right. So that will be x1 squared minus x2 squared. So as you can see, we need x1. All right. We need x1 from this equation of y is equal to 2x squared. We have to make x the subject there, right? So let us just make the subject. If y is equal to 2x squared, if we make x the subject, we're going to divide by 2 by 2. That means x squared is equal to y over 2. So you can even leave it like that because here we need x squared. So we now know that we've got x1 squared, which is y over 2. And x2 from this graph on top here, our x2 is, we're going back to the normal equation that we remember we were given here. This was the one that we made the subject, but already here x was the subject, all right, which is x is equal to 16y squared. All right, it's the same graph with the one that we had before. So here, this is our x2, which is on the negative. And like I said, this will be our x1. Already, this is x1 squared. It's being squared. Yes, we can find the square root. You will square it again, which is fine. So here, when substituting x, know that already the value there is squared. So it's going to be pi, the integral of the limits, that will be 0 to 0.125. So like I said, this x1 is already being squared. It's x1 squared, and already it's being squared, which is y over 2, minus x2 squared, which is our x2. Remember, it's 16y squared. So we are going to square that so that it gives us x2 squared. So x2 is 16y squared. So if we square this, we have to square this so that it be x2 squared. So that's 16 squared, which is 256. So that will be 256y to the exponent of 4, 2 times 2, which is 4. So we've got 256y to the exponent of 4. So this is what we are going to integrate with respect to the y in this case, all right? So you can integrate this, then substitute our limit, all right? So that will be pi in this case. Remember, here we're just going to add 1. This is 1 plus 1, which is 2. So that's y to the exponent of 2 over the new exponent times this 2. So it's 2 times 2, which will be a 4, all right? Minus, we do the same thing. This is 4. So if we add 1 here to be a 5. So that's 256y to the exponent of 5 over 5 in this case. Then we've got our limits, 0.125 and a 0 like that. So you're simply going to substitute just like previous part that we had, upper limit minus the lower limit. All right, so that's the volume. With respect to y is going to be pi, then we substitute here for the upper limit. We have got 0,125. So that's 0,125 squared over 4 minus 256 times 0,125 to the exponent of 5. All right, so this is over 5 like this, minus for the lower limit, by just looking here, guys, we are substituting a 0 here, so that is going to be a 0 there. 0 to the exponent of 2, that will be a 0 there, right? And also a 0 there. So there's nothing that you're going to have on this side, all right? So just combine for the upper limit, this whole value that we have here, multiply that by pi, you are going to have your answer as, in this case, that would be something like 0,00736, something like that, which is cubic units in this case, right? So that is your volume with respect to y. So like I said, if we are to move on together to our N6, we shall see so many things that we are going to consider on this volume, talking about the shell method, which we can write here Vy, but here it will be written dx. Then you'll be wondering what is happening on this type of a question. So we shall see those typical questions in our mathematics N6, but for this one, it's just a direct method, which is our disk method. So let us just revise as much questions as we can, preparing ourselves for the exams that are ahead of time.